What's the number here? Easy, it's 7. Your brain just processed this image and classified the number within a fraction of a second. But what if we want to replicate the human brain and its functions, specifically in a computer? I did exactly that using machine learning. Machine learning is basically just using data and algorithms to imitate the human brain. Just like how our brains use inputs, like sight and sound, processes them through neurons, and responds back through speech and emotion, machine learning receives inputs in the form of data and numbers, processes them through iteration and classification, and responds with a prediction or a decision. If you want to learn more about neural networks, check out my article in the description. I wanted to make a machine learning model to classify handwritten digits, which replicates the functions of the human brain. To do so, my plan was to train my model with a large set of handwritten digits, and for each individual digit, I use a neural network to determine patterns, and then I output a prediction from 0 to 9. I made this program using the Python language and the machine learning framework PyTorch. So here's all the code for the program. The number one step as a data scientist is to gather the dataset and understand it. For this project, I use the MNIST database, which is a collection of 70,000 handwritten digits split into training and test sets. This is super clean and structured data, which will be perfect for the accuracy and classification at the end. So before I fed this data into the model, I needed to apply some transformations to the images by giving them all the same dimensions and properties. This code converts each pixel in the image to an RGB value and adjust them to follow a specific standard and pattern. This helps in faster convergence during the training, and all the data we enter needs to have the same dimensions to enhance the neural network's ability to recognize the unseen digits. Then I proceeded to download, shuffle, and prepare the datasets for efficient use. I made the batch size into 64, meaning the model will read 64 images every time, which is kind of like the sweet spot, you can say, in optimizing the GPU storage and computing power. Machine learning frameworks and hardware are designed to work efficiently with the powers of two. Over here, you can see all the files and the data has been downloaded, and now we're ready to move on to the next step. So I wanted to show you an example image of the data so you can have a better idea of what we're working with. This is the first image in our list, and it's 28 by 28 pixels. Let's see the second one. Let's see the eighth one. There you go. Now it's time to make the neural network. It has an input size of 784, which is 28 times 28 pixels. There's two hidden layers, one with 128 neurons and the other with 64. The number of outputs are 10, which is for each digit from 0 to 9. Essentially, what this code does here is it lets a neuron output a signal only if the input is positive and is inactive otherwise. It also converts raw outputs to probabilities, which makes it easier to classify predictions. Now we're on the fourth step of adjusting weights, which I'll explain. So how a neural network actually learns is by iterating over the data multiple times in the training process. This process is called backpropagation, which calculates the difference between predicted and actual outputs and adjusts the model weight in the neural network to minimize this loss. Now, all the previous steps were to actually gather and prepare the data. Here's where the fun actually begins. This part is designed to optimize the model by updating the weights using backpropagation. Each time we iterate through this training set, we'll see a decrease in training loss, meaning our model will get more and more accurate at recognizing the numbers each epoch. An epoch is just one iteration through the training batch. Here we can see the first epoch, it has zero point 0.6, and the second one, it has drastically reduced to 0.28. As we wait, the model's weights are adjusted to better fit the training data, and we can see a gradual decrease in training loss each epoch. Here, the model learns patterns in the data and improves its ability to make accurate predictions. Now, it took about 4 minutes for this code to fully run on Google Colab. We can see that the training loss is now decreased to 0.05, which is very good for this program. Now, the training is fully complete, but how accurate actually was the model? How often did our program predict the handwritten digits correctly? Let's find out. I used the test set to calculate the number of correct predictions. And now, what we've all been waiting for. Out of 10,000 images tested, the model was over 97% accurate. This is really good mainly because the MNIST dataset I used was very clean and shuffled and it had a large quantity of data. And that's it for the code. Now, the applications of this aren't just contained in a coding environment. This recognition system is used in the real world as well. For example, banks use this technology to automate the process of interpreting handwritten numbers on checks. Apple uses facial recognition systems, specifically CNNs, for their Face ID feature. Doctors use CNNs for medical image analysis, like for detecting tumors or cancer. As you can see, there's so many use cases of image recognition in the world today. Now that I've made this project, although it's much simpler, this will eventually be used for more complex image recognition tasks. So guys, hope you enjoyed. Check out my article in the description where I write all the details and all the code for this program. My next project is a facial recognition system. We're making a program with real-time webcam feed which detects what kind of emotion I'm feeling. See y'all later.